We're in section 5.4, which is indefinite integrals. We know that we have an indefinite integral when there's no values written next to the integral sign, which is what we have here. So we learned that when we take the integral of something, it's just basically the antiderivative. And so we're asking ourselves, just like we did in 4.9, x plus 6 over the square root of x. Do I immediately know what function that I need so that when I take the derivative of it, I get that for an answer? No, I don't. That's complicated. So one thing you can do here before you do the integral or think about it is to write it in some form that you can actually answer that question. So what we can do is split this up into two terms, and we can take the integral of each term separately. So this is going to make our life easier. And so x over x to the 1/2 can be simplified to x to the 1 minus 1/2, which is x to the 1/2. And then we have plus 6 times x to the negative 1/2. So just like if we were taking the derivative, we would do the exact same steps here because we can more easily handle this function in this form. So the same is true for integrals here. We do have sort of like a power rule for antiderivatives or integrals, and so I'm going to use that on each term. For the antiderivative power rule, what I do is I add 1 to the exponent and then divide by that same value. So 1/2 plus 1 is 3/2. I'm going to put a 2/3 out front because that's the same as dividing by 3/2. And my new power is that 3/2. Then, oops, I thought I was doing a definite integral, so I started writing that in there. Okay, now from here I add 1 to 1/2, negative 1/2, and I get 1/2. And then dividing by 1/2 is the same as multiplying by 2. So I get 6 times 2 out front, x to the 1/2. And then always attach a plus c, just like we did in 4.9. And that's it. So I'm just going to write this a little bit more simplified with the 6 times 2 is 12, and I'm done. So we did this problem, or something very similar to it, in 4.9. We just have some different notation here and a little bit deeper understanding and more connections to what the antiderivative is. Let's look at another one, cosine of theta over sine of theta squared. Has this notation here. And then the variable is theta, so this second part, d theta, is indicating that theta is the variable. So this was not in that table or in your book or this highlighted blue stuff. It's not an element, there's not an elementary integral to that. So you don't throw up your hands quite yet. Just like in this part A, maybe I can simplify that in a way that I can use some things in that table. Well, here notice whenever you have combos of sine and cosine, maybe you can do a little magic here by just thinking of this in a little bit different way. So note that if you take one of the cosine, take the cosine one of the sines and write that in ratio, that would be cotangent, and then 1 over sine is another type of trig function. So maybe this will spark an answer to a derivative problem, which means then we know what the integral of that is. So cosine over sine, like I said, is cotangent of theta, and then 1 over sine is cosecant. So kind of a less common rule, but this is in the table, or the answer to a derivative rule we know, so that is helpful when you're memorizing these table of integrals or this list of integrals as I have it here. But notice cotangent right here, I could rearrange that cosecant, that it's negative cosecant x plus c. So I'm going to go ahead and use that rule and get negative cosecant of theta plus c. And I'm done. So just like with derivatives, when we are trying to evaluate an integral, sometimes some algebra is involved to be able to do that first, or it makes it easier. One thing to mention, just like with derivatives again, is we're going to go over this in more depth in a little bit, but I can't just break up an integral and do the integral cotangent times the integral cosecant. You don't have a rule that tells you to do that, and in terms of you can't do that. Just like when we had a derivative of two functions, we weren't allowed, that were being multiplied, we weren't allowed to just split it up into the derivative each separately. We had to use a product rule. We're going to have a special rule for integrals that has to do with the product situation. So you'll see that in this class, and that's something we're going to talk about next. In general, it's harder to take an integral than it is a derivative. So that's something else that we will discover through experience. So we are not doing net change theorem here formally. We did the idea with the fundamental theorem of calculus part 2 with that motivating example. So, but we aren't going to do any problems in this section. But if you have time, you can go ahead and look at that. It's worthwhile. So that's it for this section.